Hello everybody. So what we're going to talk about in this video is the second set of notes in topic 10, which is all about substitution. So as we learned about in the 10.1 notes, what we're doing now is a little bit different than what we were doing before for pretty much the whole class. Before, what we were doing was differentiation, or taking a function and finding its derivative, which expressed the instantaneous rate of change of the function as another function, as the derivative function. But now what we're doing is we're looking at integration. And while we still haven't talked about what integration does in terms of the practical uses of it, we've mentioned it a couple times. Integration, as we'll see in the next couple sets of notes after this one, can be linked to the idea of finding the area beneath a function's curve. But before we get to that, we have one more set of notes here to do just to help us talk about indefinite integrals and how to solve a couple more types of indefinite integrals. And that's this idea of substitution. So we're going to talk about this substitution rule. We're going to see how it actually links to the chain rule that we learned back in the unit or the topic 4 notes, and see how we can use it to evaluate an indefinite integral. So if we go back to the 10.1 notes, what we did in the 10.1 notes is we worked with what I like to call nice integrals, or integrals that were pretty easy to work with given how limited our integration tools were at the time. So essentially what we were doing in the 10.1 notes is we were working with integrals or things that we were integrating that either involved maybe like a power and a constant, so 8x cubed. We saw that the integral of that, the indefinite integral of that, was 2x to the 4th plus c. Something like this where we had a sum of functions of x, so 2x plus 1/4 x cubed. We could break that up by the sum if we wanted to, and then just add those two resulting integrals. Or situations like this where we had like a difference of functions of x, so cosine of x minus 1/x. And we could have broken this up by the difference if we wanted to, but here I just have it as us finding the derivative, or sorry, finding the integral all in one step. So what we've seen so far are functions that involve addition, subtraction, or just multiplying a function of x by a constant. But that limits us a little bit in the sense that what if we have an expression that involves a product of functions of x, or a quotient of functions of x, or some sort of composition of functions? And so if we take a look at these examples here, like x squared times e to the x cubed, or 2 over 3x minus 4, or 6x plus 3 over x squared plus x plus 1, if we try what we were doing in the previous set of notes with these particular forms, or these particular functions when we try to integrate them, we'll notice that a lot of the stuff that we talked about in the 10.1 notes doesn't really translate to these new or these more involved types of expressions. And so what we're going to do in this set of notes is we're going to introduce this idea or technique of substitution, which is going to allow us to work with these types of expressions and to integrate products, quotients, or compositions of functions of x. So that's what we're going to talk about in this set of notes. And so in order to understand the substitution process and why it works and what we use it for, it's a good idea to go back and think about the chain rule. And specifically, we can think about substitution as our way of undoing the chain rule. So remember in the 10.1 notes, we've really introduced this idea of integration as the reverse process of differentiation. So when we differentiate a function, we're getting its derivative. When we're integrating a function, essentially what we're doing is we're finding a function that gives the original function as a derivative. So it's like working backwards or thinking backwards. And so the chain rule was one of our very well used derivative rules. And so now what we're going to do is we're going to talk about how to undo the chain rule. So let's go back and review the chain rule a little bit. I know we're all familiar with it because we've used it so much, but let's go back to the 4.3 notes where we first introduced it and talk about what it tells us or what it allows us to do. So if I have a composition of functions, say f of g of x here, where the g of x is like our inner function and the outer function is like our f of x, so it's f of g of x, then we learned that by the chain rule, we can find the derivative of this composition of functions. And the way that we've done that is by taking the derivative of the outer function with respect to the inner, times the derivative of the inner function. So this is something we've done a lot over the past several topics. Now, again, it helps to think of integration as undoing or reversing the process of differentiation. And this helps us think about substitution in the context of the chain rule. With the chain rule, it tells us that the derivative of a composition of functions is equal to this thing. Like we just set up here, it's the derivative of the outer function times the derivative of the inner function. And so if I take this result, the result of the chain rule, and I integrate it, so I put it in my little integration notation here, the integral of the result of the chain rule should give me that composition of functions back plus that arbitrary constant c. So that's what I should be getting back from integrating the result of the chain rule. It's undoing the chain rule. It's giving me my original piece, or the thing I was differentiating, back, plus that arbitrary constant. Now, if we think about this expression, the integral part, it looks a little messy. So this is where substitution makes things look better and makes things easier to solve. So this is where we see the usefulness of substitution. So let's take our inner function, g of x, and just call it u. Then if I take the derivative of g of x, g prime of x, if I use Leibniz notation, that's like the derivative of u with respect to x. Now this is where we do our substitution. We substitute these expressions back into this integral. So this integral, I'm just re-expressing down here exactly the same thing. The integral of f prime of g of x times g prime of x. If I substitute in u as g of x, and g prime of x becomes du dx, then essentially what this allows me to do is it allows me to think about these dx terms or notations canceling, and gives me a much easier integral to work with. And then once we solve that integral or compute it, then we just undo the substitution by replacing our u back with g of x. So the whole purpose of substitution, and this is again one of those things that's a little bit easier to understand once we see it in practice, the whole purpose of substitution is trying to find some expression u where u makes calculating the integral easier. So we're going to see substitution in situations where the thing we're integrating is complicated and maybe not very easy to work with the way it is. And so what we do is we choose an expression u, rewrite our integral in terms of u, then solve the integral. So again, the whole purpose here is to make functions or integrals involving products, quotients, or compositions easier to solve by reversing the chain rule. So the reversal of the chain rule is kind of what's going on behind the scenes, but again, the thing that we want to do with substitution, or the main goal of substitution, is to make our lives easier. So we want to choose a u that makes the new integral easier to solve, making it possible for us to actually integrate the thing we want. So like I said, this makes a lot more sense when we start seeing it in practice and we start practicing picking a u. And so on the next page, what I have is I have a bunch of steps, as usual, to help us out with the process of substitution. So substitution, I remember when I took calculus the first time, I took a similar class to this way back when, I remember I had a lot of trouble with substitution because it is something that takes practice. There is no hard and fast guideline for picking u in a lot of cases. There are some things that kind of help you think about what to pick for u, but we'll do an actual example where we pick a u that's not actually going to help us, and so we have to backtrack a little bit and pick a different u. So sometimes that's what people have trouble with substitution, is it's not this hard and fast rule for picking u. But as we'll see with some practice, we start being able to recognize what's a good candidate for u, what we're looking for with u, how u helps us simplify our expression, and get to the ultimate goal, which is, of course, computing an integral. So let's go ahead and look at this example on the middle of, what page are we on? Page 3, and go through our substitution steps above with this example. So in this example, we want to integrate this function, 2x times cosine of x squared. So we want to find the indefinite integral of 2x times cosine of x squared. Now, like I mentioned, this is not one of those easy to work with integrals that we talked about in the previous set of notes. If I had tried to apply any of the rules that I learned in the 10.1 notes on their own, I might run into some issues. Because if I think about this, this is a product of functions of x, right? It's 2x times the cosine of x squared. So we're taking the integral of a product. And when our integrand, that's the name of the thing we're integrating, if the thing that we're integrating is a product of functions of x, that's usually an indication that substitution is a good way to go. So I'm going to go ahead and start with step 1. And I'm actually going to write steps 1 through 3 in a different color. I'm going to write them in green, just because this is where we're sort of setting things up with picking u and doing stuff with u before we do any sort of integration in step 4. So the first thing I'm going to do here in step 1 is this is where I pick my u. So u is just some function of x. And remember, the goal here is we want to try to find a function of x that makes my integral easier to calculate. Now, we haven't had much practice with this or any practice with this, but one thing to think about for u is try to think about it the same way you thought about using the chain rule, with this idea of an inner function and an outer function. A good candidate for u, not always, but a lot of times, is something that looks like an inner function if we were thinking about differentiating with the chain rule. And so if I think about this thing that I'm trying to integrate, and I specifically look at this cosine function, I have cosine of something, where the something is more than just x. So if I were just looking at this and differentiating it, I would think of cosine as my outer function and x squared as my inner function. Now, of course, we're not differentiating this, we're integrating this whole thing, but it kind of helps to think about things that way, because in a lot of cases, what you would consider to be your inner function in a differentiation situation is a good candidate for your u in your substitution situation. So what I'm going to do is I'm going to actually choose this x squared as my u. So I'm going to say u equals x squared. And that's all I need to do for step 1 is just pick my u. So it's some function of x, and it's not too complicated itself. It's just x squared. Now the next thing I want to do, step 2, still involves u. I want to find the derivative of u with respect to x. Now I'm going to be explicitly using Leibniz notation here, because as we'll see, that makes things a little bit easier to understand as far as what we're doing as we continue working here. So the derivative of u is like u prime or u prime of x, but I'm going to use du dx for my notation for this, again, because this makes things a little bit easier later. So I'm just finding the derivative of u, du dx, which is, in this case, just the derivative of x squared. So that's going to be just 2x. Let me move this down a little bit. So that's step 2. Finally, the next thing I'm going to do before I integrate or do any sort of integration technique is I'm going to quote-unquote solve du dx for the dx. Now, I have a note here because this is something important to keep in mind. Du dx is notation. It's the notation for the derivative of u with respect to x. So when I say solve, we're not actually solving du dx for anything because it is just notation. But thinking of solving it helps us simplify our substitution expression. So even though we're not actually solving this thing, we are rearranging it, it does help us rewrite our expression and simplify things. So I like to think of it as solve just because that's usually what we say when we're isolating an expression for something. But really, we're just rearranging it and we're kind of breaking up this notation. It almost seems like we shouldn't be able to do that. Technically, we shouldn't. But again, the idea here is this process of substitution. We're going to see in just a second how this step 3 really helps us in step 4. So what do I mean by solve or rearrange du dx for dx? What I mean is I'm going to take my expression in 2, so the derivative of du with respect to dx, and I'm going to isolate the dx. So I'm going to have it as dx equals something. That's what I mean by solve or rearrange for dx. Okay, so I'm going to treat du and dx as values, even though it's one notation. Just kind of cheat with me here. So I'm going to take the dx and I'm going to multiply both sides by dx, which gives me du equals 2x times dx. Now I want to isolate the dx, so I want dx equals something. So I'm going to divide both sides by 2x, which gives me dx equals du over 2x. Okay, so this is going to be really useful for us in just a second in step 4. So this is all the stuff I'm doing just to get ready for substitution. I've done a bunch of stuff with u, and now in step 4, I'm going to finally go back to my black ink, and I'm going to do the substitution. So this is where we write the original integrand, so the thing we're trying to integrate, in terms of u, and then we actually integrate with respect to u. So hopefully what we did is we picked a u that's going to make this thing easier to solve. And once we do the substitution, it's going to be in terms of u, but that's okay. We're going to fix that later. But the goal here, and hopefully we'll see this in step 4, is we're going to re-express our original integral in terms of something that's easier to solve. So what do I mean by that? Well, we're starting by integrating 2x times the cosine of x squared. So that's our original integral. Now I'm going to substitute, which means every place I see an x squared, I'm going to replace with u. And I'm also going to replace my dx with what I said it was in terms of du. So let's see what happens when I do this substitution. So I have the integral of 2x, that stays the same, times the cosine of, originally it was x squared, but here I'm saying x squared is u, so I'm going to replace x squared with u. And instead of writing dx, integrating with respect to dx, I'm going to want to integrate with respect to du. So I'm going to replace dx with what I said up here. It's du over 2x. Which again kind of sounds like cheating because dx is just notation. So is du dx. But, oops, sorry, this should be 2x. This piece here. So dx equals du over 2x, so I'm just replacing that here. Now, why did I do that, and what does this allow me to do? Well, if I take a look at what I've got a 2x here, and I've got a 2x in the denominator of that green expression. So I can cancel those. And what that leaves me with is it leaves me with the integral of cosine of u, and we're integrating with respect to u. So now what I've done is I've changed my notation a little bit. Now we're integrating with respect to u instead of x, so my notation's a little bit different. And my integrand, the expression I'm integrating, is different. Specifically, it's a lot easier than this. I know how to integrate cosine of u, just like I would integrate cosine of x. It's just a different variable. But I know how to do that based on what we did in the 10.1 notes. So remember, with an integral, what I want to find is I want to find what function gives cosine as a derivative. So if my derivative of a function is cosine of u, what is the original function? Well, if I think back to differentiation, I know that sine of u, if I take its derivative, it should give me cosine of u. And also I need to add that arbitrary constant because this is an indefinite integral. And so this is the derivative sorry, this is the integral of cosine of u with respect to u. A lot easier to solve, just one step, once we got to this point. Now this isn't quite what I want. I don't want the derivative with, or I don't want the integral, I keep saying derivative, with respect to u. I want it with respect to x. So that's where step 5 comes into play. Step 5 is where we undo our substitution, or more explicitly, we rewrite the resulting expression in terms of x. Meaning, every place we see a u, or something involving u, we undo the substitution by redoing step 1. Or in other words, every place we see a u, now we're going to replace it with x squared. So our final answer here, that we'll get in step 5, is the answer from step 4, except with u replaced with its appropriate x expression, which in this case is x squared. So my final answer is going to be the sine of x squared plus c. So that is the integral of 2x times the cosine of x squared. Now remember, with integrals, they're really nice in the sense that we can check our work. And I can check my work, I'll do that here with this one, by differentiating this and seeing if I get my original integrand, the thing I was integrating. Let's see if we do. Let's check it. So to check, I'm going to take the sine of x squared plus c, and I'm going to differentiate it, take its derivative. So sine of x squared, that's a function within a function, sine of something, where the something is more than x, so I need to use the chain rule. So sine of something, the derivative of that is the cosine of something, so cosine of x squared. Using the chain rule, I'm going to multiply that by the derivative of my inner function. Derivative of x squared is 2x. Plus the derivative of c, well, c is just a constant, so its derivative is 0. So what do I get? I get 2x times the cosine of x squared, which is exactly the thing I was trying to integrate here. Which is pretty cool. And it makes sense that we had to use the chain rule here because, like I said, substitution undoes the chain rule. So this thing, as we just saw, is the result of using the chain rule to differentiate something. So to reverse that, to integrate that result, we need to use the substitution rule or the substitution process. So that's substitution. Really, the big thing for us is making sure we pick the correct or a correct x, sometimes more than one x. Sorry, pick the correct u. Sometimes more than one u works. Sometimes you might start working with a u and you get nowhere, you don't simplify things, so you have to start over again. We'll do some examples of both where we kind of get stuck using a u, and the last example we're going to do in this set of notes is a case where two different u's work pretty much the same in terms of the amount of work that you have to do. So let's go ahead and do some more examples because like I said, substitution is something that gets easier the more you practice with it, like a lot of things in math. So let's take a look at this example here on page 4. Here, we want to integrate x squared times e to the x cubed. So if we take a look at our integrand, the thing we're trying to integrate, it is a product of functions of x, so it's x squared times e to the x cubed. And so this looks like it's a good candidate for substitution. So let's go ahead and start with step 1, which is again finding our u. So like I said, there's not really a hard and fast rule for picking u, but one technique that's kind of a good way to start if you're not sure is to look at your integrand and think differentiation. And think, is there a place where I would have to use the chain rule? Is there a place where I have an inner function and an outer function? And if I take a look at this e expression, I have e to the something where the something is more than just x. And so kind of like we did in the previous example, I'm going to use the something, the x cubed, as my u and see if that helps me out. Because again, the ultimate goal here is to simplify this. So let's see if picking u as x cubed will actually help us simplify this integrand and make it easier for us to compute the integral itself. Okay, so step 1, I pick my u. Step 2, I differentiate u with respect to x. So du dx, which is just the derivative of x cubed, which is going to be 3x squared. Step 3 is the weird one, the one where it seems like we're doing things that are illegal. We're going to solve or rearrange this so that we have it as dx equals something. So solve it for dx. So I'm going to multiply both sides by dx, which gives me du equals 3x squared times dx. And then I want it dx equals something, so I'm going to divide both sides by 3x squared, which is going to give me dx equals du over 3x squared. So now I have my 3 components involving u all figured out. So now let's do the substitution. In step 4, I'm going to take my original integral, which is the integral of x squared times e to the x cubed, where we're integrating with respect to x, and I'm going to do my substitution. Every place I see an x cubed, I'm going to replace it with u, and where my dx is, I'm going to replace that with du over 3x squared. So this integral becomes the integral of x squared times e to the u, and then the dx becomes du over 3x squared. Now again, the ultimate goal here is for this thing to look simpler. Right now it doesn't, but if I look at what I've got here, I've got an x squared, and then I've got this x squared in my denominator. So those two things can cancel out, which is going to leave me with the integral of, well, I've got that 3 on the denominator there. I can write that, I can write that as 1/3 times e to the u du. And 1/3 is just a constant, so I can go ahead and take that out of my integral altogether. 1/3 times the integral of e to the u, and we're integrating with respect to u. So now the integral itself, this thing, looks a lot easier to solve than this. We're just integrating e to the u, which is a nice, easy integral to calculate. So if I solve this, I have the 1/3, I'm going to leave that out there. The integral of e to the u, the function that has e to the u as the derivative, is e to the u. So this is going to be 1/3 times e to the u plus that arbitrary constant c. So nice, easy integral to solve once we have it in this form. Now remember, we're not done. We want this to be in terms of x. We want the integral with respect to x, not u. So step 5 is where we reverse our substitution. Every place I see a u, I'm going to replace it with x cubed. So my final answer here is going to be 1/3 times e to the u, which is now x cubed, plus c. Let me rewrite that so it looks a little bit nicer. 1/3 times e to the x cubed plus c. So that is my final answer. That is the integral of x squared times e to the x cubed. And I won't do it here just for time and space sake, but if you want to check this, take the derivative of it and see if you get x squared times e to the x cubed. Okay, so there's another example of substitution. Let's do another one, and then we'll do two sort of special ones on pages 5 and 6, just to demonstrate some things about the process of substitution. All right, so in this next example, we're finding the integral of the tangent of x. Now, this one doesn't look too complicated. It's just the tangent of x. But if we think about the tangent of x, what function gives just tangent of x as its derivative? And we don't really have a nice relationship with that. For a lot of our trig functions, we do. So if we go back to the 10.1 notes, we can see that in a lot of cases, when we are integrating a trig function, we sort of have a set result, right? So if we integrate sine of x, we should get negative cosine of x. Because if we take the derivative of the negative cosine of x, we get sine of x. If we integrate the secant squared of x, we get tangent of x, because if we take the derivative of the tangent of x, we get secant squared of x. But we don't have a function that when we take its derivative, we get tangent. So we don't see tangent over here on its own. We see secant squared times tangent, but we don't see tangent on its own. So this isn't one of those nice trig functions where we sort of know the result based on that relationship between the trig functions and their derivatives. So this one is going to take a little bit of work. And so the easiest way to kind of translate this into something where we need to use substitution is to rewrite the tangent function as a ratio of sine and cosine. So remember, the tangent of x can be re-expressed as the sine of x over the cosine of x. Which makes this look like a much better candidate for substitution, because now we have a ratio of functions of x. And so now this looks like a case where substitution would apply. So I'm going to go ahead and start by choosing my u. So here's a case again where maybe it's not as easy to choose u, because it doesn't look like we have sort of that function within a function sort of setup. We don't have that composition of functions in our integrand. We just have a ratio of sine of x over cosine of x. So for this one, I'm just going to go ahead and pick one of them. I'm going to pick cosine of x. If you want to try sine of x, you're welcome to. I'm going to try cosine. So I'm going to say u equals cosine of x. If this doesn't work, we can just go back and try again and try sine. But let's try cosine first and see what happens. So I'm going to differentiate u with respect to x. So the derivative of cosine of x is negative sine of x. And then in step 3, I'm going to solve or rearrange that part in step 2 for dx. So if I multiply both sides by dx, I get du equals negative sine of x times dx. Which means that if I divide both sides by negative sine, I'm going to get dx. Dx equals negative du over the sine of x. So now let's do our substitution. So we start with the integral, and I'm going to use this form here since we use that to help pick our u. We're integrating sine of x over cosine of x. And we're integrating with respect to x. So now for my substitution, every place I see a cosine of x, I'm going to replace it with u. And I'm going to replace my dx with what we set up here. Dx equals negative du over the sine of x. So this is going to become the integral of sine of x over u. Cosine of x gets substituted with u. And dx becomes negative du over sine of x. And here's really where the step where we can see if substitution actually works, if we pick the right u, because again, we want this to simplify and be easier to solve for. And we can see the way that we picked u, this sign and this sign are going to cancel each other out, which is going to leave us with negative du over u. I'm going to take that negative out. That's like a -1, so I'm going to go ahead and just take that out like a constant and write this as the integral of 1 over u. And we're integrating with respect to u. So again, this is my notation, integrating something with respect to u, and the function itself that we're integrating is 1 over u. Now 1 over u, we have an expression for that. That's one of those ones on our little cheat sheet that we talked about. From the 10.1 notes, if we take a look at page 3, if we are integrating 1 over x, the result is the natural log of the absolute value of x plus c. So here we've got 1 over u, so this is going to become the natural log of the absolute value of u plus c. So if I go back to our substitution, don't forget that -1 out in front, so I'm going to write that as negative natural log of the absolute value of u plus c. And now step 5, I don't want a u, I want something in terms of x. So in step 5, I'm going to use that result from step 4, and instead of u, I'm going to write that u as cosine of x. So my final answer is the negative natural log of the absolute value of cosine of x plus c. Now, some people are really good at integration in the sense that they can see sort of from the original thing that we're integrating what the result will be just by kind of reversing the process in their minds. So some people, maybe in this example that we did before, could look at this and say, oh yeah, I know what gives that as a derivative. Some people are really good at that. Some people aren't, which is completely fine, but some people are really good at seeing that. But I think this example is one where even if you're really good at seeing that sort of reverse process, it's hard to see, I think, that the integral of the tangent of x is this big, ugly-looking thing, or that the derivative of this is this. I think that's really hard to see. So sometimes the result you get is something that's not super obvious, even if you're really good at looking at and reversing this process in your mind. And I think this is one of those cases. Okay, so far in the examples that we've done, we've picked u's that have just happened to work. And part of that was just so that we don't get mixed up in picking the wrong u while we're still learning the process. But now that we've seen this a couple times, let's do a couple more examples where we run into some certain situations with u. So let me go ahead and go to the next page, page 5, where we're looking at integrating this big integrand here, x squared over 2x cubed plus 5, and we're told what substitution to use. We're going to use u equals x squared. So let's go ahead and do that and see what happens. So my step 1 is done for us. That's our u, so I'm just going to go ahead and label this as step 1. Step 2, this is where we differentiate u with respect to x, so du dx. Derivative of x squared is just 2x. And then in step 3, we take our result from step 2 and we solve it for dx. So that's going to give me, if I multiply dx on both sides, du equals 2x times dx. And then dividing both sides by 2x gives me dx equals du over 2x. So now we have everything we need to do the actual substitution in step 4. So my original integral is the integral of x squared over 2x cubed plus 5, integrating with respect to x. With this substitution that we chose, every place I see an x squared, I'm going to replace it with u, and I'm going to replace my dx with du over 2x. So let's see what that does for us. So this is the integral of x squared, that becomes u, over 2x cubed plus 5, and my dx becomes du over 2x. Now, like I've mentioned, this is the point where we want to start seeing things simplify or cancel each other out. And if we look at what we've got here, I can't really cancel anything. There's nothing about this that looks simpler or easier to work with. And so here I'm like, what do I even do from this point? And if you run into this sort of situation where you get to step 4 and you do your substitution and it doesn't look like anything's canceling or simplifying each other out, that usually just means that the u you picked might not be the best choice. So this u equals x squared that we were told to use might not be a good choice because it doesn't really help us do anything here. It doesn't simplify things, and that's the whole purpose of substitution, is making the integral easier to solve. So let's try again. Let's integrate the same function, but now let's use the denominator as our u. So now our step 1 is saying u is equal to 2 times x cubed plus 5. And let's see if this does anything better for us. So step 2, I'm going to differentiate with respect to x. So if I differentiate u, what I'm going to get is I'm going to get, using the power rule, that's going to be 6x squared plus the derivative of 5 is just 0. So du dx here is just 6x squared. So in step 3, rewriting this so I have it as dx equals something, I'm going to multiply both sides by dx, giving me du equals 6x squared times dx. And then dividing both sides by 6x squared gives me dx equals du over 6x squared. So now let's do this substitution and see if we get anything nicer. I'm integrating x squared over 2x cubed plus 5. And here, every place I see my denominator, so 2x cubed plus 5, that's going to become u, and dx is going to be du over 6x squared. So this becomes the integral of x squared over u times du over 6x squared. And this looks a little bit better, right? Now I've got some things that it looks like I can cancel out, specifically that x squared term. I've got this 6 on the denominator here. I'm going to write that as 1/6. So this is going to be 1/6 times, I'll write it as du over u. 1/6 is a constant, so I'm going to go ahead and take that out. So I get 1/6 times the integral of 1 over u, and we're differentiating with respect to u. So now this kind of looks like the one we did above, right? This one in the previous example, where the integrand is just 1 over u. So this looks a lot easier to solve. If I integrate this, I have the 1/6 there. The integral of 1 over u is going to be the natural log of the absolute value of u plus c. And so in step 5, I undo my substitution by noting that u is 2x cubed plus 5. So I'm going to replace my u in this expression with 2x cubed plus 5. So my final answer here is 1/6 times the natural log of the absolute value of 2x cubed plus 5 plus c. And so the takeaway from this, just to kind of demonstrate it in class before you see it in person, if you end up seeing it in person, is that some substitutions may not work in the sense they don't simplify things. They don't give you an easier integral to evaluate. So if you run into trouble using one substitution, don't worry about it. Just go back to the start, step 1, and pick a different u. Try a different one. Because sometimes, like we just saw, there's a u that doesn't work very well, doesn't actually allow us to simplify anything, and there's a different u that makes our lives easier in terms of solving the integral. There are certain situations where different substitutions may all still work and give you a decent integral to solve with the same amount of work depending on the u that you pick. And so that's what we're going to look at in the next example. So here on page 6, our last example, we are integrating 1 over x times the square root of the natural log of x. Now that doesn't look like a very fun function. Looks like it's rough to integrate. So let's try substitution, and let's actually try 2 different substitutions, 2 different versions or values of u, and see that they actually give us the same result. So this is just us demonstrating that there are some cases where different substitutions will work. It just depends maybe on what you choose for u. Maybe some people see a u that works for them, another person sees a different u that works for them, but they both ultimately work just as well as the other one. So I'm going to go ahead and start by labeling this one version 1. And we're going to try to pick a u here, and then in version 2, a little bit further down the page, we're going to try a different u. So I'm going to compress things just a little bit here so that we have enough room on the page. So I'm going to do steps 1, 2, and 3 sort of in a row here on this page. So let's pick a u. So if I'm thinking about, let's say, my denominator here, and I'm thinking about like an inner function, I have x times the square root of the natural log of x. So specifically, if I look at this square root of the natural log of x, it's like the square root is my outer function, and the natural log of x is like my inner function. And like I said, we really don't have that sort of situation here because we're not differentiating this, we're integrating it. But as we've used this before, it's a good way to pick a u. Think about an inner function and pick that as your u. So I'm going to go ahead and say u equals the natural log of x for this first version and see what that gets me. So in step 2, I differentiate that. The derivative of u with respect to x is going to be 1 over x from the natural log of x. And then in step 3, I want to solve this for dx. So let's multiply dx to both sides. So I get du equals dx over x. And again, I'm just doing this all in one line here. If I multiply both sides by x, I'm going to get dx equals x times du. So now let's do our substitution. My original integral is 1 over x times the square root of the natural log of x. And so now, every place I see the natural log of x, I'm replacing that with u, and dx is being replaced by x times du. So let's see what that gives us. This is the integral of 1 over x times the square root of u times x times du. Now this looks like it's working. I can cancel this x with this one, which is going to leave me everything in terms of u. The integral of 1 over the square root of u du. Now let's see if we can make this something that looks a little bit easier to integrate, because right now that integrand still doesn't look very nice. But if I remember my square root function, I can rewrite that as u to the 1/2. And since it's on the denominator of a function like this, I can rewrite this as the integral of u to the negative 1/2. And now this is a lot easier for me to integrate. It still looks kind of rough because I've got that negative exponent. But if we go back to the 10.1 notes, remember that we had that nice little form for integrating x to the n. So I'm going to go ahead. This is page 3 of the 10.1 notes if you want to flip to it while we do this. I'm going to use this little formula here to integrate u to the negative 1/2 because it's of the form x to the n. Okay, so my n in this case is negative 1/2. So if I integrate this thing, I'm going to have 1 over n plus 1, so 1 over negative 1/2 plus 1, times u to the negative 1/2, my n plus 1. And then, of course, my plus c. That looks a little rough, so let's see if we can simplify that a little bit. 1 over negative 1/2 plus 1, that's 1 over 1/2. And then I've got u to the negative 1/2 plus 1, that's 1/2 its power. 1 divided by 1/2 is 2. So 2 times u to the 1/2 plus c, which, let me put that square root back in there instead of the power of 1/2. This is 2 times the square root of u plus c. So in step 5, as usual, what I'm going to do here is I'm going to replace my u with what I said it was in terms of x, the natural log of x. So my answer here is going to be 2 times the square root of the natural log of x plus c. So that u seemed to work pretty well. I had to do a little bit of simplification around this part here just to get it into a nice integrand, but it ultimately worked and it wasn't too hard to integrate. But maybe you looked at this and you said, okay, I didn't pick the natural log of x. I picked the square root of the natural log of x, that whole thing as u. Does that work? Well, let's check. So version 2, we're going to do this whole thing again. But now, instead of our u being the natural log of x, let's pick the square root of the natural log of x as our u and see if that works. So this is the same thing as the natural log of x raised to the 1/2. So step 2, I'm going to differentiate that as usual, the derivative of u with respect to x. I need to use the chain rule here. So my outer function is the square root of something. So the derivative of the square root of something, or the derivative of something to the 1/2, is 1/2 of the something to the negative 1/2. And then my inner function, the natural log of x, the derivative of that is 1 over x. Now I'm going to rewrite that just so it's a little bit nicer looking, so it's easier for me to solve for dx in the next step. Let's see. So what's on my denominator here? Well, this 2 from the 1/2, that's on a denominator. 1 over x, the x is on a denominator. And the natural log of x is raised to the negative 1/2, so that can be on a denominator as well. So I can actually rewrite this as du dx equals 1 over the 2 from the 1/2 times the x from the 1 over x times the times the square root of the natural log of x. Because 1/2 as a power gives us the square root. It's negative, so that square root of the natural log of x goes on the denominator. So step 3, let's solve this thing for dx. Multiply both sides by dx. I get du equals dx over 2x times the square root of the natural log of x. And then multiplying both sides by that denominator gives us dx equals 2x times the square root of the natural log of x times du. Okay, so let's do our substitution again. So let me write down that original integral. Our original integral was the integral of this thing up here, 1 over x times the square root of the natural log of x. So that's square root of the natural log of x. That's going to become u, and dx is going to become this big thing here. So what do we get? We get the integral of 1 over x times u times 2x times the square root of the natural log of x times du. So we see a cancellation here. This x is going to cancel with this x, but notice that we still have an x in this expression. We don't want that. We want everything to be in terms of u. So initially this might look like it doesn't work, but if we consider the square root of the natural log of x, let me use purple. Actually, let me use orange. What is this? This is u. So I can actually replace, I have kind of like a spare square root of the natural log of x. I can replace that with u. I can do another substitution. I don't have to do the whole process again. I just need to note that every place I see the square root of the natural log of x, I can rewrite that as u. So this becomes the integral of 1 over u times 2 times u, taking the derivative with respect to u. And now things start to look really easy because the u's cancel each other out, and that actually just leaves us with the integral of 2. So we actually get a really easy integral to solve here, the integral of 2, and we're integrating with respect to u. And so if we're integrating a constant, the thing that gives that constant as a derivative is going to be the constant times our variable. In other words, 2 times u plus that arbitrary constant c. And so in step 5, we replace u with what we said it was up here. U is the square root of the natural log of x. So our final answer becomes 2 times the square root of the natural log of x plus c, which, if we scroll up a little bit, I think I can fit both of these on the page, yep, we get exactly the same answer we got using the natural log of x as our u. So here's an example, and I just wanted to do this just to show that this can happen. There are cases where you could pick two different U's, and they both work. They both involve slightly different amounts of work or places where the work happens in the question, but they both give you the correct answer. They both simplify the integrand enough that you can calculate it based on what you know from the 10.1 notes. And again, that's the whole purpose of substitution, is making the integral easier, or basically making it at the level that we saw at the 10.1 notes, so that you can compute it using the information that you have from 10.1.